We are going to start our notes on the next topic. And what it is it's basically kinematics, but now we're doing things in 2 dimensions rather than 1 dimension. Last time, throughout the entire year, all of our problems have been things moving in one direction. Whether it changes direction or not, it's still moving either up and down a hill, straight up and down in the air, or straight left and right. Now we're going to look at things that will actually curve in their motion. There are two kinds that we're going to look at. One is a special case called projectile motion, and the other one is circular motion. So the difference is projectile motion is a fancy way of saying things that are flying through the air. So if I launch a catapult, if I let something roll off a table, if I throw something in the air, it's basically saying something that is just flying through the air. So the only thing that's really affecting it is the force of gravity, which is trying to pull it down. More details about that in a few minutes. And the other one is circular motion. It's exactly what it sounds like. It's things that are going in circles. What we're going to focus on now is projectile motion, this special case, because we can apply a lot of old things that we know, and it's really not too much of a stretch of what we're trying to do here. So let's review, let's talk about examples of projectiles. We said a couple already. A cannon shooting something up at an angle when it's flying through the air, a ball rolling down a hill and then leaves up at some angle off a ramp, still going to fly through the air. Again, we're interested in this part where it's just flying through the air. And let's say we got a ball and it's rolling off down a ramp off the table. You guys are actually going to do this in class probably a couple of times. But those are some examples. And it really just means something that's freely moving through the air. So now, I got ahead of myself. Now let's review kinematics. Because we're going to use the exact same equations that we did when we talked about acceleration and a little bit about net force. But we're going to apply it to a very special case. And here's our example to brush up a little bit. I have a rock that's sitting on the edge of a cliff, and the cliff is 20 meters tall. And it's sitting just on the edge, so if you bump this thing, it's going to just fall straight down. And if this object falls straight down, how long does it take to hit the ground? All right, this is going to be the foundation of how we do these problems. So let's review how to do this. We need to write down the things that we know. Explicitly, the only thing that's given here is 20 meters, but there are a few other things that we can figure out. For example, we know the initial velocity is 0. This is basically the same model of dropping something from rest. So that initial velocity at the very instant it's dropped is 0. We know the distance it's going to go is 20 meters. And if this is falling through the air, we already know what the acceleration is. We know that it's 10, and it's going straight down. So key thing to remember is it's always pointing down. And the question is, what is the time? So now we need to look at our 3 equations that we use a whole lot and decide which one we can actually use that will help us. So let me erase this. So here's one. We have our final velocity. So final velocity equals initial velocity plus acceleration times time. We have one that's similar, where we have initial and final velocity, acceleration, and position, but it still doesn't really quite help us, so let's look at our third one. And this last one will be the one that we'll have to use, because the first one, we don't know what the final velocity is, so that equation has too many unknowns. Same problem with the second one. We don't know the final velocity. But the third one, we can simplify that to where it's useful. It starts at 0, so we can say it starts at 0, and we know that initial velocity was 0, so both of those things will drop out, and we're going to use just the side on the right. So our equation is going to simplify to this, 1/2 at squared. And we know what x is, we know what a is, we can solve this for t. So solve this for t. Alright, so a little bit of algebra, and isolate t, and then we want to plug in our numbers. Again, this is just quick algebra. And when I plug in everything I know, and actually get a number for this, I get to about 2 seconds. So it takes 2 seconds to fall that distance. Okay. It helps with these problems if we are actually looking at something that's moving in 2 dimensions. We want to separate x direction and y direction. And the thing that we conclude is that there's no acceleration in the x direction. So that means whatever that velocity ended up being, it's going to stay the same throughout the whole time. So velocity is constant. And in the y direction, we know the acceleration always is 10 meters per second down. So our acceleration is constant. Alright, so let's go through an example. So I'm going to roll a ball off a table, and it's going to leave perfectly horizontally. So that means our initial velocity here is exactly in the x direction. So here's our problem. How far is it going to go? If it leaves the table at 2 meters per second and the table is 1.3 meters high, how far does it go? So we're going to look for this variable x. So the x distance from the edge of the table to where it lands, this is what we're interested in here. Okay, so let's do what we did before. We're going to break up the x stuff and the y stuff. So I already know what I'm looking for in the x direction. This is what we're mostly interested in. We're interested in x, and I know the x velocity. And in the y direction, I know a few things. If this leaves perfectly horizontally off the table, then that means the initial velocity in the y direction is 0. This will be like the same thing as dropping something straight down. And the acceleration is 10 meters per second down. So remember, this is always true for projectiles. We're going to basically work backwards here. We want to use this equation. We want to use this equation to get our distance, because we know that the x velocity is constant. So if we can find how long it takes, we can plug it into that equation. So our goal here, and again, the height is 1.3 meters, so our goal is to find the time. And this is how we do it. Find the time, plug it back into that equation. Alright, so this is how this works. I'm going to show 2 different examples here. And in class, you will see some demos and some videos to show that this really is true, and I'm not just making this up. So if I dropped a ball straight down and compared it with a ball that I shot horizontally, and I did them both at the exact same time from the exact same height, then at every moment in time, they are at the same height no matter how fast I shot it to the right. So if I shot it really fast to the right, it's still going to be at the same height as the ball that went straight down at every second. So this will help us. So the time it takes to fall straight down is exactly the same amount of time that it takes to hit the ground far away from the table. So what we're going to do, like in our example of finding the time where it fell straight down, we're going to do it again. All right, so let me go back. So we know those are our variables, and these are all in the y direction. So since we know the time it takes to shoot off the table is the same amount of time it falls straight down, we're going to solve the problem of how long does it take to fall straight down, because it's the same amount. So we're going to use that same equation we did before, but I'm going to start using the letter y to talk about the vertical distance. Okay, so that's our vertical distance. And this problem is pretty simple. We're just going to solve that equation for t, and then we're going to plug in what we know. So once we do this, we get about half of a second. Okay, so we have the time it takes to leave the table and hit the ground. So I'm going to plug it back into that equation where we know the velocity in the x direction is a constant. So solving this equation for x and plugging in velocity and time, we know that it goes about 1 meter away from the table. Okay, so there's a basic example of horizontally launched projectiles. We're going to do some more labs and more challenging questions while we are in class. But this right here, this is the basics. Here's the main idea.